look at random vectors, but I'll try to cover what is necessary in order to understand the common filter next week. Okay. So what do we mean by random vectors? So we normally say random vector is just a vector of a number of random variables. Okay, we can just say that x is, well, it can be x, it can be whatever, right? Let me put, instead of x, no, let me put it as maybe n. So it's more generic, okay? And so let me change all the x here to be n, so that they will not interfere what we have later. Oh, sorry, let me put x. Sorry. Let's do x. Otherwise, I have to change so many places. Okay. Okay. So let us consider a vector with all the x here are random variables. Okay. So that's all for the random vectors. Okay. So xi, they are random variables. Okay. And what are the random variables? Well, you can look at for an example. I'm not going to go into super detail. Let's say I have x1 is a random variable with a uniform distribution. Okay. Okay. So in time domain, if this is the continuous, so x1 probably has some values, but it's unpredictable. Okay. Because it's random. Okay. So we often try to explain in terms of PDF. So we often explain in terms of PDF, like f of x, 1 of x. Okay. And see what they are. Okay. If they are uniform distribution, typically it means that the value will tend to be within a certain range, say A and B. Okay. So this is the PDF, which is in a way similar to a histogram. Okay. And if it's not a uniform, but it's a Gaussian distribution, if it's a Gaussian distribution, okay, then the PDF is gonna be, well, depending on what the mean value is. If it's Gaussian distribution with the mean of uh, mu and then the variance of sigma square, okay, then the PDF is gonna be something like this. Okay, centered at the mu, and then the sigma square or variance, it will determine like how spread the values are. Okay, so if you plot x1 and then t, you probably have values like this. Okay, so sigma square, in a way, it determines the spread, how the values fluctuate. Okay, so in MATLAB, it means that if we have this type of values, let's say x1 is ran in 1000, and you plot what it is, probably see something like this. Okay, so it's unpredictable, so it's not deterministic. Okay, so you cannot tell what it is, but you can find the mean and the variance. Okay, you can find the mean of x1, you know, like in this case it's about 0. You can find the variance of x1 as well, you know, and you get something like near 1. Okay, if you want to generate these signals random values, let's say you want to change the mean to be like 5, and you want to make the variance to be like 1.6, you just put square root of 1.6, which is 0.4. Oh, is it right? No, let's say you want like a variance of 4, you put a square root of 4, which is 2, and multiply, and then you replot again. Okay, and you will get something like this. Okay, so it's shifted. The mean is not 0 anymore. It's shifted to about 5. Okay, and because they are not so predictable, so we often try to compute something like plot like histogram of x1 and x2, right? So let's take a look. I don't need to open. I don't need to open all these windows. So let me put it here. Okay. So you get something like this, but then it doesn't look so nice, So let me put the number of the number of bars to be more than just 10. Make it 30. It will look a little more. It's not exactly Gaussian, but it's somewhat similar. So you can see that it has this type of the mean is about 0, and the variance you cannot tell much here. Okay. You can also do the same thing, but then you can plot for x2. Okay. You know that for x2, the variance is higher. So when I plot it, notice, capture this on your eyes. And then if I plot the histogram, so this is what it is. Okay. But maybe not, maybe better to compare on the same plot, right? It's a bit easier to see. Okay. And then I don't know whether it's easy to compare, but anyway. Okay. Oh, well, they look at the values the same. Okay. X1, X2. So the spread here is -2 to 2, but here the spread is from about 0 to 10. So the spread is larger for the bottom one. Okay. And so that's it. And so in general, these are the random variables. So if you have different types of random variables, it's easy to just look at the PDF or the histogram. Okay. The only difference between histogram and PDF is that for histogram, it on the x-axis is the amplitude, and then on the y-axis is the number of counts. Okay. But then for PDF is similar to histogram, but the vertical, the y-axis is the probability values, and that's the main difference. Okay. So for PDF, what it is on the y-axis, this is like is the probability density. Okay. For continuous random variables, we cannot find the probability of each value. It's the probability density, right? But if in Matlab, when we plot it, it's always discrete, right? So on the y-axis is actually, instead of probability density, is the probability values. And so that's the, so different types of random variables you cannot predict, but you can always look at PDF, and so on. Okay. And then if you have multiple random variables, like in this case, you have x1, x2, xn, and so on. Okay. You can find the relationship between two random variables. Let's say x1 and x2. You can find the relationship. Let me see how much I should talk about. Okay. So actually, before looking at relationship between x1 and x2, just random variables, let's look at this. We can find the mean of x1. Okay, we can find the mean two ways. One is find the what is called expectation, which is integral of x1i and fx1 x1 dx. Okay. But if it is discrete, you can just sum. Like in Matlab, you just sum. You don't do integral. No, summation of x at each value. This is x1, right? At each value and multiply with its probability. Okay. And I is equal to 1 all the way to whatever values. Okay. You just sum whatever it is. Okay. For the variance, you can find it similarly, but the variance is the sometimes called sigma x square. Okay. In terms of integral, it's just integral of x1 minus the mean. I can call this as mu1 square and multiply with the PDF. Oh, no underline, no? This is not vector. We'll go into the vectors in a minute, okay? But then for discrete, you can just summation of x1i minus mu1. Mu is just a constant value, okay? And multiply with probability of x1i, where I is equal to 1 to n. Note that this I is not time, okay? Is the index of the possible amplitude. Let's say if you talk about like coin tossing, you only have two outcome, okay? So I is like the index of possible outcome, okay? Okay. If xi is x1 is like the number of 1 to 10, but they're random, you cannot tell when it's going to be 1, when it's going to be 2, 3, 4, then I is equal to 1 to 10. That's all. Okay. But you can generate x1 like infinitely, but the values are in between 1 to 10, just like that. Okay. So this is the index of the possible outcome. Okay. So you can define for x2 similarly, okay? So whenever we see this expectation on the computer is all sum, this is called expectation, okay? It's like a, here it's like a, you can call it like a statistical average, okay? Okay, so what are the relationship between x1 and x2? We can find various things. For example, we can find what is called correlation between x1 and x2. Okay, we can write it as R. I guess x1, x2 is okay. So this will measure the relationship between x1 and x2, like whether like they are, they have the same trend or not, or they are not so easy to predict. Okay. So if uh, 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 correlation. Actually, let me call it. Yeah, let me call it. I can call it like this. So what is this? This is just the expectation of x1 multiplied with x2. Okay. Or is the summation of x1i times x2i. Okay. And multiply with the probability. This is joint probability. Don't worry too much. We're not going too much in detail here, but I need to say it anyway. Okay. So, okay. So this is the concept. You try to we find the trend between x1 and x2, whether one can tell from each other. Okay. But in Matlab, it's very simple. In Matlab, you can just compute everything according to time. Okay. You can just multiply x1 and x2 and then summation and average. Okay. So on time domain, it's very easy. So on time domain, you can just find r of x1 and x2, okay, by summation x1 at each time times x2 at each time, okay, where t is equal to 1 to, I don't know, infinity or too much, no, to nt, okay, and then divided by and normalized to 1, okay, and divided by, I think, uh, okay, and normalize it, okay. But anyway, so in general, if you normalize it, you have something like this. If correlation between two random variables, if it's equal to 0, we say they are orthogonal, okay. If it's and if is equal to 1, it means x1 is equal to x2. If it's minus 1, x1 is equal to minus x2. Okay. On average, no, on average. Okay. But in general, r of x1 and x2 is between minus 1 and 1. Okay. So let's take a look. See if I compute this in Matlab like earlier. Okay. Let's take a look. So what do I do here? Okay. Well, I can compute in Matlab. I can use the command so-called xcore for x correlation. You can use help to find what it is. I understand that you all probably knows about this. Okay. So uh, so this is the how to use correlation. Xcore is actually cross correlation. Cross mean is between two random variables. Okay. So so you can just do xcore between two random variables or two vectors in essence. Okay. And we can put some option. Okay. Here we can comma bias, non-bias, normalized. When you normalize it, it's the same as correlation coefficients. Okay. And if I do bias, I have to scale the values by 1 over m. Okay, I think that's the length. And if I do unbiased, I scale it with 1 over m minus absolute value of lags. Okay. So let's take a look. Earlier we plot x1 and x2, right? So earlier we have x1 and x2. Let me do it. Okay, no need to plot again, right? Because we saw it already. So let me try to compute x core of x1 and x2 and see what I get. Okay, but I also want to put the the option coef, so that is the maximum at 1. Okay. Okay. Also, when you do cross correlation, they try to find the let me see. Maybe I should write it easier. I see. Let me go to this page quickly. Okay. So in Matlab, when we use Xcore, this is what happens. Okay. So in Matlab, okay, when you use the command called Xcore, this is what it does. So if we have X1, okay, in time domain, and we have X2 in time domain, okay, what it plots is like this. It plots correlation of X1 and X2 between X1 and X2 at different time lag. Okay. Let's say that this is X1, this is X2, okay. If I put time lag, let me put tau, right? Tau, let's call time lag as tau. If tau is 0, I just multiply them one by one. I multiply this value at this time with this value. So I look at the same time. That's what I do. This is T1, this is T2. And I just multiply the two values at each time and then sum, okay, and then normalize it, okay. But if I have tau is equal to 1 or minus 1, I have to shift x1 or x2 by one sample, okay. So for this part, I multiply x1 at time, let's say time of 2 seconds. I multiply with x2 at 2 seconds, okay. Let's say this is the 2 second, 4 second. I multiply the same time. But when tau is equal to 1, I multiply x1, let's say at 3 seconds, with x2 at 2 seconds. Okay. So I have a time shift of 1. So when I use X correlation, what it does is like this. R12 of tau is equal to the average of x1 t times x2 x times t plus tau and then x2t. Okay, so that's the difference. Okay, it's a time lag. So it means that when I use Xcore, if I want to have time lag 0, I just look at the maximum values. Okay, in the middle. It's in the middle. So let me go to Matlab quickly. So if I come here, okay, and I use this value, okay, I can do Xcore. It gives you a huge dimension. Let me do it as the C, okay. Oh, R, okay, R. I'm not gonna plot it because it's huge, but it has the dimension of 1 times almost 2000. Okay. But if I plot it, this is what I see. Plot of R. What I see. Okay. 0.02. Okay, so it's very small. So it means that it's not very related. Okay. If I do R2, but I compare it with itself, okay, if I compare with itself, I should get 1, right? R, oh, okay. If I correlation. If you have no time lag at all, you just multiply. They're the same values, right? Then you get huge maximum correlation. But if you shift x1 by just one sample, two samples, because they are random, it's not no correlation. It's not easy to predict. Okay. So here, if I do this and I plot it again, and I plot the rx1, this is what I have. So I will have a maximum value at, oh, I use the value in the middle, sorry. Yeah, at the 10, at the 1000. Yes. So I use, so the correlation of x1 with no time lag with itself, this is 1. But if you shift time by one samples and then you do correlation, you get almost 0. It means that from one sample to the next, it is super difficult to predict what it is. Okay. So that's about some review on random variables. Okay. But very often, instead of finding the correlation, which is r x1, x2, and tau, okay, we can find very often time when the mean of x1 is not equal to x2. When like think about stock markets, stock price. Some companies have very high value, some very low. When you look for relationship, sometimes it's better to remove them. Okay. So this is like the average between x1t plus tau times x2t. Okay. But for covariance, let me call it as C. It's the same, but we subtract the mean from each random variable. Okay, it's the same, but I subtract the mean first, and then I compute the correlation and minus mean. Okay, this is minus. So that's the only difference. Okay. So this is when the mean, sometimes very different. That's how we do it. So if I go back to Matlab and I can compute similarly, okay, but I need to subtract the mean, right? So what I do is I'm gonna find a correlation again, like that, between two values, okay? But I will subtract the mean of x1. I will subtract the mean of x2, okay? And I can call this C for C12, no? Instead, this is called covariance. And if I plot this, C12, we will use the value at the 1000, okay? That's how it's computed here. Okay, so this is it. So this is value at 1000. Covariance is still small. Okay, the thing is because x1 and x2 they are random and they are not related. So wherever you find it's very small, no matter which time lag you use, it's so hard to predict among each other. Okay, and okay, lastly, let me go to what we looked at earlier. Because we say that the random vector is just the collection of the random variables, right? Okay. So let me see. Okay. I'm gonna go into too super deep, okay? But I want to review enough so that we can take a look at it later and work on it. Okay. So if I let x is equal to x1 and x2, okay, where x1 and x2, they are random variables with the mean, with the variance, with the PDF, and so on. Okay. If I want to find, we can find so-called correlation matrix. Okay, you get something like this. So let me see. Should I write it like this? So for correlation matrix, we will write it as Rx. Okay, this is the average of X times X transpose, which is the average of X1 times X1, X2, and transpose, we get X1, X2. Okay. So in general, if this one has the dimension of m by 1, okay, so this correlation matrix will have the size of m by m. It's called matrix. Actually, you know, in when you type it, if you type on your paper as a matrix or vectors, it's all bold, right? Bold colors, bold face. But when I write it, if it's a matrix, I often try to put 2 lines so that we know that they are matrix, no, they're not vectors. Okay. So what is it? Correlation matrix is a matrix that contains correlation between x1, 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 x2, x2, x1, and x2, x2. Okay. So that's a correlation matrix. So it is the correlation between x1 times x1, x1 square, x1 times x2, x2 times x1, and x2 times x2. Okay. So this is the what is called the correlation matrix. Okay. And so if you put the average inside, okay, you can look at it as the statistical average or just the time average. They're similar. So you get something like this. X1, X2. Okay, we can find this from what we saw earlier, right? X2 times X1 or X1 times X2, they are the same. And like this square. Okay. So this is the what is called the correlation matrix. Okay. We find relationship between x1, 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 x2, x2, x1, x2, x2, and we just put them in matrix. So that's what it means. Okay. And let me see. So these two terms, because it's the correlation of itself, we often call autocorrelation. Okay. And for these two, we call cross correlation. Okay. Okay. So this is for the correlation matrix. But similarly, look at one property. What happens to R transpose? What is R transpose? Okay. One property is that the R transpose is equal to R transpose X. Okay. So actually for correlation matrix, there are two properties. Okay. Number one, R transpose. This is the matrix, no? I put 2 underline. Oh, not these are, sorry. This is like the real numbers. Okay, is equal because they are symmetric. Okay. And second property, I don't think I have time to prove. It has the property called positive definite. If you're interested, you can search on the web. There are many. There are many sources. Actually, it has the property of positive semi-definite. It means that given a vector k, okay, for any vector k, we can put k transpose multiply with r and k, okay, for any k matrix. It's always greater than or equal to 0. Okay. Please put the box around it. Okay. Do you see this come up again next time? Okay. And additionally, if it turns out that this k times matrix or correlation matrix and k is greater than 0, in such a case, we call it as positive definite. Okay. Okay. Similarly, instead of defining just correlation matrix, let's define a covariance matrix. Okay. It's the same as correlation matrix. So for uh, covariance matrix, okay, we just find the covariance of x1, 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 x2, x2, x1, and x1, x1. Okay. And okay, so let's define it as C of x is equal to the average of, I use an example of x1, x2, no, just for simplicity. And then x2 minus mu2, okay. It's going to have the same size as well, which is the m by m as well. It's the same as correlation, but it has this minus mean, okay. So if we write it out, we have something like this. Okay, so we have x1 minus mu1, x2 Oh, sorry. If you look at the definition of autocorrelation, it's the x times x, no? But inside x, you have x1 and x2. Sorry. Okay. Okay. So x is x1, x2, and the vector for the mean is mu1, mu2. Okay. So you can think about it this way. When we talk about random vectors, it's basically talking about multiple random variables. Okay, we're talking about a number of random variables, but we put them in vectors. Okay, just for easy processing. That's all. That's all it means. Okay. Okay. So from the definition, we can write it like this. Okay. For x minus mu, we have x1 minus mu1. Okay. And x2 minus mu2. And we do the same, but we change the from column to row. Okay, so that's all we do, and we have the same thing with the correlation matrix. Okay, so first I have x1 minus mu1 square. I have x1 minus mu1 times x2 minus mu2. Then I have x2 minus mu2 times x1 minus mu1. And lastly, I have x2 minus mu2 squared. Okay, so it's the same as the correlation matrix, but with the mean term here, 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 here. Okay. So what is the first term? If I put in the expectation inside, the first term is just the sigma value of x1. Okay. Second term, I can write it as C12, right? And this term, I can write it as C21, or C12 is all the same because you can switch order. I can write as C12. Okay. And lastly, I have sigma 2 square. Okay. So this is the covariance matrix. Okay. Okay, let's see how much further should I go. I think for random vectors, that's about it. I'm not gonna go too deeper than these. Okay, otherwise it's gonna be forever. Okay, so what I can do is let me look at the set up the property for you. Okay, so for the covariance matrix, it has the same properties as Rx, same properties of as correlation matrix. Okay, meaning that one is symmetric matrix, and also two, it has the positive definite matrix. Okay. So, okay, lastly, I'm going to talk about this quickly. Okay, I'm going to set up the problem for you so that next time when we look at the Kalman filter, then you know all these property for use. Okay. So given that we have a system where input is x, okay, and we have a system as A is the matrix, let me put double line, and then we add it with some bias vector, okay, and we get a y, okay. So in this case, we can write it as y is equal to ax plus b, okay. Here we let x to be random vector. Okay, you can think about data. Data can be random as well. That's why we don't know what they are. Okay, and for b can be considered as a fixed number or constant vectors. Okay, so if I want to find the property here, let's say I want to find the mean of y. Okay. So I would say that mu y is equal to expectation of y. You can think about expectation as average, okay? Expectation of ax plus b, okay? But because expectation is average, it's linear, okay? It's expectation. So in time average, it's just the sum and then divide, okay? It's linear, so we can write it as expectation of a times x, okay? A is a matrix, x is a vector, and then plus the expectation of the bias, fixed number, not random. Fixed mean not random. Okay, so here we can write it as a times mean of x plus b. Okay, because b is not random, so we can just write it like that. Okay, and 2, so this x has a related values of vector of average. It has the correlation matrix. It has the covariance matrix, which contain all the properties, okay, of the we can call this as the first 2 order of average, okay. So for the y, we will often ask what is average of y and what is R y, C y, for example. Okay, let me look at the next one and we finish. Okay, so what is for y? What is the autocorrelation? What is the correlation matrix? What is the covariance matrix? Okay, so let's do Ry first. Ry is just the expectation of y times y transpose, I think. Yeah. Okay. Y is a times x plus b. Okay. And a times x plus b transpose. Okay. So this will be a times x plus b and x transpose a transpose plus b transpose. Okay. Then I just multiply them out. Okay. So what I will get is the average of a times x transpose times a transpose, which is this term multiplied with this term. Okay. And then add it with a x times b transpose. Okay. Note that we cannot change order of multiplication of matrix and vectors. Okay. And then plus b x transpose times a transpose, and then plus b times b transpose. Okay. Here we can write it out as, we can expand expectation inside. So first term we have a times expectation of x times x transpose and a transpose. Okay. And then plus the expectation of these 2 terms. Okay. This term, the size is m by n. Oh, wait, did I put m or n? Let's do n by 1, no? Otherwise, it doesn't match. Okay. So the size here is m by n, and x is n by 1. Okay. And b, okay, b transpose is 1 by n, is it? Okay. I think it's right. So these two become m by 1, right? And this is 1 by m, so the whole thing is m by m. This thing is just a transpose of the first term as well. Okay. I don't know, can we do any more from here? Let's see. So we have many terms here. Let's see, does this term collapse? M by n, n by 1, m by 1, 1 by m, with m by m. I guess it's okay. Yeah, it just has a lot of term. Okay. Because it has the b here. Okay. Uh, let me see if there's anything else I can reduce. I guess not. Yeah, I guess it has a lot of terms here. Okay. That's fine. That's fine. Okay. But let's say that if the bias is 0, if the bias is 0, okay, then what we will have is the correlation vectors, correlation matrix. It will be only the first term, which is A times expectation of X times X transpose and then A, okay, or Ry, no, not Rx. But this term is Rx, okay, from definition. So we get A times Rx, and then I think A transpose, right? Okay, A transpose. So this is what we will get if the bias is not 0. Okay, if it's 0, if it's not 0, you get this term. If it's not 0, then it's more complex. Okay, and but then for covariance matrix, and we finish here. But then for covariance matrix, so this is what it is. Or for y, no, not x. So we have expectation of x minus mean, right? Oh, what? Sorry, y minus mean y. Okay. For the covariance, it will be nice. It will be easier in terms of terms. Is y minus mu y times y minus mu y transpose. Okay. But then y is a multiplied with x plus b. Okay. But the mean, what is the mean? The mean is a mu x plus b. Okay. Plus b with the minus, it becomes minus. Okay. And similarly, okay, so you find that for the first term, okay, this thing canceled out. Okay, so you get a times x minus mu x, which is the signal, random vectors minus the mean, right? So here it will be a times x minus mu x transpose, okay, because they canceled out, so easier for me to write this way. And if I transpose it, I get x minus mu x transpose times a transpose. Okay. Then I can do the same thing. I can because A is not is not random. I can move the average to the random part, which is here. And then A transpose, okay? Because the A is not random, so we can pull outside. Okay. And you notice that the middle term is just the here, it's just the covariance of the x, okay? Covariance matrix. So it means I can write it like this. That is, C covariance of the y is equal to A. Okay. A times covariance of x times A transpose. Okay. We will use this next time, so please put a star to it. Okay. So for this one, it doesn't. Okay, you can use it. And yeah, so we'll use this next time. Okay, when we do the Kalman filter, which is an example. So hopefully we finish not so late next time. Okay. Okay, so next time is the on Kalman filters. So please review the lecture this time, and so that when we look at, but Kalman filter is not super difficult. If I don't derive much, I can use the property today on covariance. Then I am okay. Okay. So in that case, next week's not gonna be super difficult, but once you know this property, then that's fine. Okay. So please stop recording. We are done today. Do you have any question today? Anyone? Sorry, maybe I went through a bit.